So hi everyone, I would like to welcome you all to this talk of the IEEE GRSS-APS student chapter at the University of Southern California. Today we are pleased and honored to have this talk presented by Professor Vladimir Okhmatovski, entitled On Higher Order Imperative in Computational Electromagnetics. Professor Vladimir Okhmatovski received the PhD degree in antennas and microwave circuits from the Moscow Power Engineering Institute, Moscow, Russia in 1997. From 1998 to 2003, he was a postdoctoral research associate with the National Technical University of Athens and the University of Illinois at Urbana-Champaign, respectively. In 2004, he joined the Department of Electrical and Computer Engineering at the University of Manitoba, Canada, where he is currently a full professor. His research interests are the fast algorithms of electromagnetics, high-performance computing, modeling of interconnects, and inverse problems. He authored and co-authored over 150 technical papers, book chapters, and patents in the areas of computational and applied electromagnetics. Professor Okhmatovski has been an active volunteer for the IEEE Antennas and Propagation Society, serving as a chapter chair of the IEEE Winnipeg Waves chapter from 2006 to 2011, and as chair and co-chair of the Membership and Benefits Committee of the IEEE APS since 2018. He was a recipient of the 2017 Intel Corporate Research Council Outstanding Researcher Award. He was also a co-recipient of the Best Paper Award at the 3rd Electronic Packaging Technology Conference in 2001 and Outstanding ACES Journal Paper Award in 2007. Now we shall start the talk, and Professor Okhmatovski, the floor is yours. Thank you.
All right, Michelle, thank you very much for this introduction and for the invitation to give the talk. I am excited to deliver this message, and hopefully there will be some good learning experience here for the students and professionals attending. And nice to see some of the colleagues and good friends and former students, current students in the audience. Welcome, everyone. Thank you for taking time. And the topic of today's seminar is the high order imperative in computational electromagnetics. And I would like to start from acknowledging the group of students who are working with me in this area over quite a number of years. This is Mohammed Shafipur. I would like to continue with the acknowledgement of the students who worked on various projects, which I'm summarizing here and trying to draw some conclusions from. So it's Mohammed Shafipur, Jonathan Aronson, Ian Jeffrey, Reza Galami, Zhutong Cheng. And those are all the guys who really put the hard work over the years into the results I'll be showing and attaining the understanding of the concepts which we've been exploring. And we have been all, and I'm currently a professor at the Department of Electrical and Computer Engineering at the University of Manitoba in Winnipeg, Canada. And the outline of my talk will be to first to introduce my group at this point, to show you what type of problems we are working on and what kind of applications we are interested in. Then talk about the motivation for the high order electromagnetic analysis. The focus of this talk is the high order imperative in the computational electromagnetics. That is the next item on my outline here. We'll also tell you about so-called Rockling's dogma, which is quite an important set of rules, which some people are not familiar with. Then we'll talk about some of the key ingredients which go into the large-scale analysis, error-controllable analysis of radiation and scattering problems. We'll talk about some technical details on error-controllable geometry representation, error-controllable high-order discretizations, and error-controllable fast algorithms. Then we'll show some numerical results and draw conclusions to this work. All right, so just a few words about my research group, which specializes in computational electromagnetics at the University of Manitoba. So here are some of the applications. I put pictures of typical representative cases from some of those applications we've been working on. One of those areas is in the high-order electromagnetic analysis, which we started really somewhere in 2007, and that was initially funded by the Department of National Defense in Canada. And that's the reason most of our examples here will be of this military nature. We also work quite extensively on electromagnetic analysis of the power systems, and specifically looking at the problems of the charge draining into the soil through the grounding systems of the power installations, and doing full wave analysis of those three-dimensional structures situated in layered medium of the Earth. We have done quite a bit of work in electromagnetic analysis of the interconnects, and this is a large scale modeling scenario here of IBM plasma package, where the goal is to perform characterization of the interconnects within this package. And we have done quite a bit of work in analysis of the structures with integral equations in layered media. So we worked on Green's functions of the multi-layered media, and formulation of integral equations with multi-layered media kernel. And we also have done quite a bit of work on solution of the inverse problems. Again, to most of these aspects, I will not be paying any attention in this talk, and we'll be focusing on the higher order analysis, and I'm hoping to deliver a message on the benefits of doing analysis in higher order as opposed to low order methods. And I would like to acknowledge my current students in the group: Shucheng Zheng, Christopher Phillips, Zimbo Li, Osman Ghani, Jamil Ferosh, Amit Babazadeh, and Masa Shah. So those are students who contributed to various of the projects in the past, and this is the current composition of my group. All right, so with that, let me move on to the motivation of the needs which we have today in electromagnetic modeling. And as an example, I would like to start from SBIR. So this is a small business research initiatives in the United States from 2015. It's a bit outdated, but that was a $1 million US Navy SBIR announced back at the time, where the goal of the project was to analyze structures in the range of hundreds to 1,000 wavelengths in electrical size for the models of the aircrafts, with all of the antenna models on board of the airplane, okay, and deliver the accuracy of simulations within 5 digits of precision, okay, and that precision was required in the modeling of the near fields. So if you look at solution of this type of problem, it's actually presenting a grand challenge, and I would venture to say that even for the commercial tools of the day, delivering electromagnetic analysis with 5 digits of accuracy in the near fields for 1,000 wavelength targets with 50 onboard antennas would be a grand challenge. As a matter of fact, most of the tools wouldn't be able to do. Okay, but the demand for this type of simulations is out there. It's needed. And what I will be discussing today in this presentation, if you wish, is a roadmap to attaining this type of solutions. Okay. So just to give you an idea why such a precision in the simulations is required, I want to show you an example here of an airplane model and the signals induced in the antennas. So you'll have one antenna, inverted F antenna, so-called, sitting on the top of the airplane, and the other one sitting on the belly of the airplane. And what you see here on the graph is the induced signal from plane wave incident on this airplane model on these two antennas. Okay, so this red curve will be signal induced in the antenna in the lead area, and the blue curve will be a signal induced in the antenna in the shade. Okay, so what you'll see, this blue curve is actually magnified 100 times. Okay, so if you draw it down to the level where it is, what you see is that as you analyze these large-scale targets, electrically large, there is a huge dynamic range in the electromagnetic fields which you have to capture. So within this simulation, you would have to capture 5 orders of magnitude in the disparity of the fields, okay, because the fields in the deep shade of the target would be substantially smaller than the fields in the lead area. Okay. And in order for you to be able to predict fields within this type of dynamic range, you get this requirement for high precision of the solution. Okay, so this large electrical size is what creates high dynamic range. Okay, and the requirement for the precision is largely stipulated by resolving the fields in the well-illuminated areas compared to the shade areas. And if you think of the 50+ antennas of different communication and radar systems sitting on board of the airplane, those antennas, they influence each other, right? There are EMC, EMI issues which need to be predicted. And in order to predict them accurately, this type of analysis needs to be done. So that's where we're coming from with theories and algorithms, which we will be discussing today. It's the drive to perform analysis with this level of demands on it. So let me show you now a few examples here of electromagnetic analysis performed on a canonical structure. So we're taking a sphere here, and we'll be analyzing radiation problem of electric dipole hanging above the north pole of this sphere with a low order method, which is a classical RWG method of moments, and high order method, which is called locally corrected Nastran method. And I'll say a few words about locally corrected Nastran method, how it works in the subsequent slides. So for now, I just want to illustrate the difference in how much accuracy you can deliver into your solution from low order method compared to the high order method. So what we are looking at here in the plots, in the 3D picture, you see the distribution of current on that sphere due to the dipole hanging above the North Pole. So the size of the sphere is 33 wavelengths in diameter. And what you see here is this plot of the magnitude of current as a function of the angle. So the 0-degree angle, we are at the North Pole, at 180 degrees, we are at the South Pole. And naturally, you can see that the field at the South Pole is several orders of magnitude lower than the North Pole near the dipole, because the South Pole sits in the shade. Okay. So we have me-series solution for this problem, which gives us a reliable reference. And so what we are doing here, we are taking RWG method of moment solution of the problem with 9 triangles per wavelength. and looking at the error in our WG method of moment solution compared to V series. So this blue curve here is showing to you the error in the solution, where we average this error per 20-degree interval of this scope of angles from 0 to 180 degrees. So what you'll see is that in the lit area, you'll get yourself reasonable error, somewhere within 1%. And as you climb deeper down into the shade area, the error will be increasing. And once you get to the deep shade, it will be as high as 30%. Okay. So if you go ahead and push your number of unknowns further, so here you are getting yourself 11 triangles per wavelength. Now you have 3.6 million unknowns in the solution of this problem. Well, the error dropped somewhat, but you can still see that in the shade area, you are having very high error. So now let's see what you get yourself with a high order solver. So if you take locally corrected Nystrom solution of the order 15, which will have 442 roughly 1,000 unknowns, you get yourself accuracy of the solution at about 10 to the power minus 6 level from lit area down to the shade, and you can see beautifully resolved deep shade fields on that sphere. Okay. So if you were to obtain this type of accuracy of the solution, and that's what I'll illustrate in the next few slides, with RWG method of moments, you would require approximately 10 to the power 13 unknowns. Okay, so which is staggering number. It's not something anyone can really simulate today on the largest supercomputer with best fast algorithms. This is just beyond the reach. Okay, so what I will be talking about today is how we can perform the accurate solutions and what the challenges are. Okay, and also we'll try to explain to you that a lot of commonly used conventions and notations are really incorrect. So if you look at the error behavior in your solution in the high order solver versus low order solver, in the ideal scenario, your error will be scaling as h to the power p. Okay, the h is going to be size of the discretization. I'll just jump one slide ahead. So if we have this high order discretization of the object, so h will be the size of the elements. Okay, and the p will be order of polynomials approximating solution within each of those elements. Okay, and to show you that indeed in the properly constructed solvers, the error will behave according to this h to the power p formula, I'm showing to you this plot here, which shows the high order locally corrected Nystrom solution versus inverse of the size of the elements. Okay, and what you see here is that the trend in the error, as we refine the mesh, basically we are making the size of the elements smaller and smaller. Okay, so 1 over h gets larger and larger as we go along this x-axis here. And what we see here is that as we refine the mesh, our error in the solution will go down. And as we increase the order in our solution, the trend in how fast that solution goes down will be increasing. Okay, so that's a log-log scale plot, and that signifies this h to the power p error behavior. Now notice that you have these constants a and b. Okay, so you may have, say, a MFIE solver converging with error as h to the power close to 2p, whereas electric field integral equation solver will converge as h to the power p, for example. Okay, so these constants depending on discretization scheme you are using and type of integral equation you are solving, they may be different. Okay. Now, what follows from this dependence of the error on the step size h and the order p is that the number of unknowns, okay, in the solution of your problem will be scaling with accuracy of your solution epsilon. That's what you are prescribing. So in this case, for example, we will be prescribing 10 to the power -6 error level. So with the given order of the solver P, the number of unknowns will be scaling according to this formula here. So let me move on and show to you the implications of it. I already had a bit of an introduction to what to expect. We already saw that 15th order high order solution getting 6 digits of accuracy with 500,000 unknowns, whereas RWG method of moment lower solution would achieve this kind of accuracy with 10 trillion unknowns. Okay, so let's go take a look and start understanding what the difference is and what the common misconceptions are when people talk about complexity of electromagnetic solvers, electromagnetic engines. So if we look at this complexity scaling and start from behavior of error, which we already discussed in the previous slide, where the error in our solution will be dropping as h to the power p. Okay, again, h is size of the mesh, p is the order of polynomial approximating our solution in integral equations will be currents on the surface of the object, surface of the scatterer. So the number of unknowns in such high-order solutions will be proportional to order of discretization p squared. Naturally, that if our solution, for example, is 3, then we will have 3 degrees of freedom over one dimension, 3 degrees of freedom over the other dimension. So overall number of degrees of freedom will be 9 in accord with the order of discretization. So that's where that p squared is coming from. And the number of unknowns will be inversely proportional to h squared, where h is the size of the mesh. Again, that's understandable. So if we look at the surface, if we reduce the size of that patch 2 times, the number of patches on a given geometry will go up 4 times. Okay. So that's just basic explanation why the number of unknowns scales as p squared over h squared. Now let's perform the following experiment. So if we take 2 different solvers, okay, let's say RWG method of moments and high order Nystrom method. Okay, let's take 2 different solvers, just as we were looking at them before here in these examples for radiation of a dipole near sphere. And assume that one solver which we are working with will have size of the mesh h1, okay, and order of discretization on those elements p1. And the other solver, let's say the solver 1, which we are considering here, let's think of it as RWG method of moments, okay? And the other solver will be a, say, high order solver, say, locally corrected Nystrom method, which will have size of the mesh h2. And again, we're talking about smooth object with size cumulatively being quasi-uniform across the geometry. We will talk about complications and deviations from it as we move along with this discussion. But for now, just let's look at this hypothetical simple scenario with a sphere, uniform discretization. We have 2 solvers, low order solver with step h1, p1, and high order solver with mesh size h2 and order p2. Okay. Now, if we go ahead and say, all right, let's equate the error which those solvers produce. Okay. We'll take the error produced by the solver 1, say RWG-MOM, and equate it to the error level produced by the high order solver. Okay. Then what we can easily obtain is the formula which you see here, which will relate now number of unknowns which we are going to have in the low order solver, okay, which we would have to commit in that solver in order to get the same error as our high order solver, which has number of unknowns n2. Okay, and P1 and P2 are going to be the orders of discretization within those respective solvers. So this is the formula. So you can, type it in MATLAB quickly and see what it actually tells you. What will tell you is the following: that if you were to fix the number of unknowns in a high order solver, let's say to 10,000 unknowns, and started to increase the order of your solution from 3 to 6 to 10, and you could take different numbers here, right, with the different orders of the solution. So basically we would be jumping here from curve to curve to curve. In the previous plot I showed you for error convergence for sphere. Okay, that's what is happening here as we fix number of unknowns and we increase the order in the high order solver. And then we'll be monitoring how many unknowns the low order solver will require in order to provide the same accuracy in the solution. And the trend you will see is immediately going to tell you that your number of unknowns in the lower order solver will be growing exponentially. Okay, so look at this. We're fixing here the order in the solution to 2, okay, in the lower order solver. And why I'm fixing it to 2, just to show you roughly again the trend and error in RWG method of moment solution. You can see this dashed red line, RWG-MOM, for this solution of the radiation problem on the sphere. And here's the first order solver, which we have from the locally corrected Nystrom method. Here's the second order solver. So it looks like this red curve is doing something like order 1, maybe a little bit better than that. Okay, so let's give it order 2. And according to this basic relationship where we equated the errors produced by the low and high order solvers, what we are seeing is that the number of unknowns which is required in the lower solver will be growing exponentially fast. Okay, where the number of unknowns in the high order solver is fixed, and we are just increasing the order of discretization on the patches. Okay, and this is what you see here as the effect of what we already discussed before, where we looked at 15th order solution, getting a 6 digits of precision within 500,000 unknowns, and getting RWG method of moments to require 10 trillion unknowns for achieving the same accuracy. Okay, that's the same trend which you are seeing here. Okay, so the conclusion which comes from this is that estimation of algorithm complexity without notion of accuracy is actually incorrect. Okay, so if we, for example, constructed n log n high order solver, let's say we have an order 6 solver where number of operations which goes into solution of the problem scales as n log n, whatever we did. Error controllable fast multiple method with locally corrected Nystrom discretization or something else. All in all, that's what our complexity scales as number of operations in the 6th order solver. So what that means is that if we take order 2 solver, okay, which scales with n log n complexity in its own unknowns, then in the unknowns of this high order solver, it's really scaling as order n cubed log n. And that's something what you immediately see from this formula which we are discussing. Okay, so your high order unknowns, for example, if you take order P is 6 and order P1 is 2, the unknowns of the high order solver will be to the power of 3 with respect to the unknowns of the lower solver. So if you're looking at order n log n RWG method of moment solver, really that solver scale is order n cubed log n in the unknowns of the high order solver of, in this particular example, solver of order 6. Okay, I hope you see that. And oftentimes in the computational electromagnetics community among engineers, you will see, order n log n MLFMA solvers, for example, without really a notion of accuracy brought in. So the best people will offer you is that they have, say, 10 basis functions per wavelength, per linear wavelength in the mesh. Whatever accuracy they come up with, there is usually no notion of that. Whatever that RWG method of moment delivers to you, that's what you get. So what you need to appreciate is that n log n scaling of the lower solver is really in the scaling with respect to the unknowns of a high order solver. If you took order 6 solver, would be really a solver which is scaling as n cubed log n. So basically, number of iterations going into obtaining solution of the same accuracy in this lower solver would be exponentially higher than number of iterations which you would be requiring from your computer solving the same problem with high order solver. So that example, again, can be illustrated well. I just put a bit of a real life kind of illustration here, dollars, okay, currency. So if you say I have $10, okay, just equivalent to you saying, okay, I have 10 million unknowns I can solve with my solver I put together. Unless you specify what kind of unknowns they are, in what kind of solver, that notion that you can solve 10 million unknowns doesn't really go far. And here's an example to illustrate it to you in tangible terms, that if you have US dollars, like high order unknowns, or you have Zimbabwe dollars, then you'll see that banknote of the Zimbabwe dollars with $1 trillion on one banknote, okay, which will buy you as much as $1 US. Okay, so you saying, okay, I have $10 without saying whether those are Zimbabwe dollars or US dollars, really say nothing about what you can get with those dollars. And that's just an analog I want to bring up here in talking about the unknowns which you can handle in your solver. In the sense that if you have 10 million unknowns you can handle in high order solver, those high order unknowns will go way further in terms of what you can get out of them than 10 million unknowns in the lower solver. Okay. So this is to illustrate and give you some examples which are prelude to what is referred to as higher order imperative. And that is something which I took from slides by Stephen Wanzura. And the high order imperative was formulated by him as these three notions which you see here. So first one is that equating the size of the problem to the number of unknowns is incorrect. Okay, so basically handling the problem with 10 million unknowns and what those 10 million unknowns can get you may be very different depending on what kind of numerical scheme, low order or high order you have those unknowns associated with. So second notion here is that estimate of computational complexity without notion of accuracy is meaningless. Okay, so if you say that my computational complexity scales as order n log n in your solver, but you do not specify with what kind of accuracy, you don't have accuracy in this complexity scaling, that type of information is meaningless. And that's what you saw in the example I was illustrating in the previous slide. So if you say you have order 2 solver with n log n complexity, really in the terms of the unknowns of the high order solver, you're really dealing with n cubed log n complexity. Okay. And the third item here is that higher order algorithms are exponentially more efficient. And this is what you see simply by analyzing the simple formula and equating the errors which you obtain in the solution from solvers which are scaling with h to the power p type of error behavior. So one more plot here to illustrate this formula, which I showed you in the previous slide, where we look at number of unknowns scaling when we require certain accuracy in the solution epsilon, that would be error, and we have order p of the solver. So let's look at how this number of unknowns will behave depending on order. So here's our unknowns. Over x-axis we have order of the solution, and we are plotting this scaling a number of unknowns for different levels of required error. Okay, so if we have 2 digits of solution which we are requiring, that's typically what would be expected from, say, RWG method of moments. What you'll see is that the number of unknowns which you will be required from solvers of different order are not going to be varying all that much. Okay. As you tighten your accuracy requirements, and now say you want your solutions to be obtained with 4 digits of accuracy, okay, and you look again at this scaling in number of unknowns versus order of the solution, what you'll see all of a sudden that your lower solutions, here's your order 1 solution, order 2 solution, they will start requiring exponentially higher number of unknowns than the number of unknowns which you would require from your high order solvers. And you can continue this trend, plot the same curve now for 6 digits of accuracy, which you require. And that's where the numbers are going to start getting staggeringly high for lower solvers. Okay, so you will see that if you're requiring 6 digits of accuracy and you are attempting to solve the problem with first order solver, like RWG method of moments, then you are getting yourself into trillions of unknowns, whereas high order solvers will give you half a million unknowns type of requirement for achieving the same precision. Okay, so this is a numerical illustration of what is behind these notions which go into this high order imperative formulated by Stefan Wanzur. And for those of us who worked with low and high order methods, that's becoming very apparent. And we can appreciate those rules by looking at how the solutions behave. All right, so that's the focal point of my message. I will be now from this point on talking about various complications, because the world I described to you where the error in the solution behaves as h to the power p, that's the ideal world we want to live in as numerical analysts, and we are building our solvers to scale like this, despite the complications which we face. Solving problem of scattering on a sphere is a trivial task compared to solving the problem of scattering on an airplane with 50 antennas on it and requiring the same accuracy of solution. So next item I would like to show you is Rockling's dogma. Again, I took this, this is a copy of a slide from Steve Van Zurer, fellow who formulated high-order imperative. And he formulated Rockling dogma. So Rockling, most of you here in this audience will know who that is. That's the creator of fast multiple method. And fast multiple method was named one of the top 10 algorithms of the 20th century, alongside with FFT, QR decomposition, and other few famous impactful methods. And Steve Van Zurer, who was his collaborator, Rockling's collaborator, that is, for a number of years, that's how he formulated Rockling's dogma. So you can think of this dogma as a set of rules which are preserving integrity of scientific computing. So let's go over the items in this dogma. So first item is methods must be fast. Okay. What does that mean? Well, if you solve your scattering problems in electromagnetics with integral equations, and say you use your method of moments or other discretization scheme, you can populate your matrix and just go ahead and do direct LU decomposition solve. It will give you order n cube scaling, where n is number of unknowns. Or you can go ahead and accelerate your solution with hierarchical matrices or fast multiple method or FFT type of solvers, and all of a sudden your complexity will drop to say n log n. Okay. Again, we need to talk about the error level, right, for n log n to be meaningful, but that's the idea here, that when you solve the problems and there are fast algorithms, you do not want to be solving them directly. Second item, errors must be controlled. Okay, so what that means is that approach where you do something what we do in RWG method of moments. Okay, let's take 10 triangles per wavelength, cross our fingers, and see what comes out of it. That's a lousy way to construct numerical solution. Okay, so if you were to construct the algorithms which allow you to predict the error in different areas and control it, that takes the whole new ballgame. Okay, and that's how it needs to be done. So errors must be controlled. Now methods must be high order. Why? That's what you saw in previous slides in the high order imperative discussion. It's because the high order methods are exponentially more efficient. Basically, a number of operations going into the solution of the same problem with the same accuracy requirement with higher order method will be exponentially cheaper than solving the same problem with low order low order schemes. Now, discretizations must be point-based. Some of you who worked with fast multiple method may know that you could just work with the RWG basis functions directly and push them into your tree, as opposed to coming up with point-based discretization, pushing points into the tree. There's a big difference. Matter of fact, if you look at it carefully, what you will see is that your fast algorithms will be suboptimal if you do not work with point-based discretizations. Now, formulations must be well-conditioned, and this is a tricky business. But basically what Rockling is telling us is that when you solve a problem, say with integral equation method, what kind of integral equation you solve makes a big difference. You know, like in the example of that dipole radiating near sphere, you must appreciate that you could solve it with electric field integral equation or magnetic field integral equation or combined field integral equation, or perhaps you could construct some Calderon preconditioned integral equation, right? What is the difference? Well, the difference actually is huge, because depending on what kind of formulation you are using for solution of the problem, the spectrum of that integral equation will be different depending on the formulation. Okay, and if your spectrum of the integral equation in its continuous non-discretized form is inherently not sustaining type of solutions which you would like to have, then you will be limited in what you can get in this type of integral equation formulation to begin with. Okay, so that's the item which motivates work with less trivial, more complicated, but better behaved formulations of the integral equations than the obvious choices such as EFIE, MFIE, and CFIE. Okay. Last item, God did not invent polynomials, he invented exponentials. You can come up with your interpretation here, but my understanding here is that really you should be striving for exponential error behavior in the methods you are constructing, as opposed to the polynomial error behavior. Okay, so basically, whether you're filling out matrix elements or you're constructing fast algorithms or coming up with discretization schemes, you want your errors to be exponentially dropping as you tune the knobs controlling this particular scheme. And here, nice footnote, any deviation will be regarded as an escape attempt. Guards will shoot without warning. So basically, if you go ahead and start putting together some lousy schemes which are ignoring these basic rules for properly constructed algorithms, you're really out for lunch. You are into the woods somewhere, and your scheme really will not be competitive compared to the state-of-the-art best type of solutions which are available. Okay, so that's Ropling's dogma. Again, I'm just reciting to you and giving you my own interpretations, give it some extra thoughts, and can also discuss it as part of this talk. All right, so I'll present next a few challenges, and I need to wrap up my discussion here soon. So what we have talked about so far is this idealized scenario where we have nice smooth scatterer, we have h to the power p error behavior. In reality, when we look at the complicated models such as airplanes with realistic models of antennas on them, we don't have that. We will have sharp edges. Okay, we will have curvilinear edges and few other issues. So let me just show you some of the challenges here which construction of this type of solvers faces. Some of them are more obvious than the others. So we have large dense matrix equations, obviously. We have electrically large structures. We have large disparity in the field levels in the shade areas versus lit areas. Again, that's that high dynamic range we talked about before. We do have the breakdowns in the integral equation formulations which we are solving. Oversampling and low frequency breakdowns are there. We have poor conditioning of the matrix equations, which result from the discretization of those continuous integral equations, which are of three basic mechanisms, such as physical resonances, oversampling, and low frequencies. And the big challenge going into construction of high-order solvers is also associated with accurate evaluation of the matrix elements on general curvilinear meshes. Okay, so those are the challenges with different degrees of difficulty in resolving them. So I wanted to say a few words about locally corrected Nystrom method, for which I showed already quite a few results. Just briefly what it's about. if we look at the electric field integral equation here, so we have current as our unknown on the surface of the scatter. We have the Green's function here of the electric field. And in electric field integral equation, we're really saying that the tangential component of electric field on the surface has to be 0. And what locally corrected Nystrom method will do, it will split the surface into the elements, patches. And within each patch, it will sample current with quadrature points. So then effectively our integral with this Green's function, the current will be represented with the summation which you see here. And you can cast a solution of your original continuous integral equation into the form of solving system of linear algebraic equations which you see here. Okay, so you'll be solving it with respect to the weights of the current and the quadrature points of each of the elements. Okay. So that's the high order scheme. Very briefly, there are lots of complications to it if you go into details, but that's what we refer to as this locally corrected Nystrom method. So a few results which we've been obtaining in my research group. So here's the numerical results for solving the problem of scattering on a sphere with order 4 solution. A bit over 6,000 elements, 300,000 unknowns, solved in parallel with parallel fast multiple method, accelerated locally corrected discretization. And so this type of solutions, again, according to the previous discussion, is what would require from RWG method of moments solution with 4 billion unknowns if you were to get the same accuracy. Okay. I'm going to skip details on the parallel MLFMA solver, which we were constructing with error controllable operations, something we can discuss later. As I promised in the outline of the talk, I will say a few words about error control representation of the geometries. There is quite a bit of interesting research going into that. What I wanted to mention here is the discretization of the geometries with NURBS, which are non-uniform rational B-splines. And this framework is very well supported these days by the CAD packages. Specifically, we were using Rhino CAD tools for construction of those high-order representations. And there are libraries which allow you to formulate position vector on each of those elements, sub-refine the mesh. And this type of geometry representation is fully high order, it's curvilinear. It does have the challenges though. And some of those challenges are that when you merge those NURB surfaces on a complicated geometry, they really don't come together exactly. You'll see some small gaps between them. So you basically, the geometry is not airtight. So that's a bit on the representation of arbitrary geometries, which we've been dealing with. And here's one of the examples of a spiral antenna model with locally corrected Nystrom method. So where we're showing that this h to the power p error behavior you can get not just for a sphere, you can actually get this type of error behavior for more complicated three-dimensional geometries. But once again, you can see that here when we have ends of this geometry, we're actually smoothing them out, right? We do not leave them with sharp corners, because in sharp corners, you will have singular behavior of the fields, of the currents, which you have to properly resolve, and which will actually kill your h to the power p behavior in the error unless you take care of those edge singularities. But we can see in principle for smooth, sufficiently smooth geometries, you can get yourself a three-dimensional objects or h to the power p error behavior. Some of the comparison of the Nystrom method, again, higher solution versus lower solution, and really the message here I wanted to deliver is that for non-smooth objects, you have a very good benefit in terms of number of unknowns. You get compared to lower solution from your high-order solvers, even when you don't care for controlling accuracy down to very deep levels. Okay. So here we are showing a fifth order Nystrom solution with 40,000 unknowns, which gives roughly the same accuracy as RWG method of moment solution with 1.2 million unknowns. Okay. That's the message where with 1-2% error kind of requirements, the higher order methods are beneficial in just simply reducing how many unknowns do you need. All right, so error control in the multi-level fast multiple method, I'll skip this for further discussion. We'll show you a bit what we are working on right now. So we are working on construction of fast direct solvers based on the hierarchical matrices. As a matter of fact, we are collaborating with Professor Sideris from USC on it. And some of the results are shown here, how we get the memory and CPU time scaling in the solver, which is of order n log n nature, whereas we are solving the problem with h to the power p error behavior. What you see here as an example for a sphere with n log n complexity scaling, and we do it without the troubles of iterative solvers giving us poor convergence. So challenges and solutions and conclusions. And this is the end of my talk. Sorry, I'm going a bit overboard. So quickly we'll go over the challenges which we are currently facing. So the challenge of the large dense matrix equations, we have fast algorithms. H matrices are robust, not n log n at high frequencies. Basically, as frequency goes higher, ranks grow up, and that n log n nice complexity will break down. Fast multiple method, n log n nicely behaving with high frequencies as well, iterative in nature, which means that as you take complicated geometries, things fall apart, and iterative solver may not converge. Disparity in level of the fields, that is taken care of by the error controllable matrix field and error controllable fast algorithms. Handling the fields near curvilinear edges, that's a big challenge. So you can either construct the custom quadrature rules, which are very efficient but not general, because for general curvilinear edges at the junction of general materials like metal dielectrics, you will not know what that exponential behavior of the singularity is. So practical solution here is really HP refinement of your meshes, which is general, but creates majorly imbalanced algorithms and expensive schemes. Now for the breakdowns, which we have in the integral equations, there are Helmholtz decomposition-based methods. For lower methods, they're well developed, such as loop tree, loop charge kind of basis. They're hard to generalize for higher schemes. And the promising approach are different formulations of the integral equations based on the Calderon identity, so-called decoupled integral equation formulations, which allow you to overcome those inherent breakdowns to, say, EFIE and MFIE. Poor conditioning of the matrix due to physical resonances. This is something which you can handle nicely with fast direct solvers. It will give you robust solutions, but much more expensive than what we would get with iterative fast solvers like MLFMA. Now, as far as computation of the matrices, matrix elements with error-controlled behavior, there are semi-analytical methods which are efficient, not general, or you can do brute force adaptive integrals, which are robust but very expensive. So with these conclusions, higher solutions are exponentially more efficient. Controlling error in large-scale higher solution requires error-controllable representation of the geometries, error-controllable evaluation of the matrix elements, and error-controllable acceleration schemes. All of that, just like in the chain is only as strong as the weakest link in it. That is how in the error controllable algorithm, the algorithm is only as strong as the least accurate part in it. Okay. So, and all of this hinges on conditioning of the matrix. So if conditioning of the matrix is poor, then even if you use well-tuned fast algorithms, matrix field schemes, it will put it all under major strain if the conditioning of your matrix due to natural resonances or breakdowns is poor. So with this, I will stop this talk, and hopefully we'll have time for a few questions.
Thank you so much, Professor. This was such a nice talk. I think I need to go back and watch the recording one more time to digest all the details. So the floor is open. Shaswat, you want to unmute yourself and ask the question?
We have also one question before that, I guess.
Sure, we'll address that.
So Roja asked, what is the significance of higher order methods in antenna design and how can we implement it?
Well, when you come to the antenna design problems, higher methods are already there. As a matter of fact, if you look at the software by company Tikra, they have higher method of moment solution. And the need for this type of solutions is well justified. If you are looking at prediction of the radiation patterns of those antennas, where your side lobes are very accurately resolved. So imagine you have some main beam of a parabolic dish, and then you have side lobes, which are somewhere at, say, minus 80 dB level. Okay, what that means is that your fields radiated in the off main beam direction will be 4 orders of magnitude lower. So imagine now that you need to have, say, 1% error in resolving those side lobes of your antenna radiated field. So that requires 6 digits of accuracy in your numerical scheme. And what you saw, if you were to go ahead and discretize this antenna with, say, RWG method of moments, and were to get 6 digits of accuracy out of it, you will end up with billions and if not trillions of unknowns required. Okay, that's where the need comes in for higher resolvers.
Great. So the next question is saying, could you comment on LCN versus higher order vector basis function in terms of the accuracy efficiency trade-off?
Well, that's a good question. And one thing I want to mention in relation to this question is that the Nystrom schemes, I'll put it in plural, schemes, they can be made exactly relatable to high order method of moment schemes. We've done some of this work with my former student, Mohammed Shafipur, and specifically we were looking at the RWG method of moment and its relationship to locally corrected Nystrom method, which I was discussing here. What you can show is that you can take method of moments matrix and construct it out of matrix of the locally corrected Nystrom method and construct that method of moment matrix with machine precision accuracy with respect to it being constructed without Nystrom method. So what I'm trying to say in few words is that if you have yourself higher order discretization or according to the Nystrom method, which is point-based, in principle, you can construct such conversion of bases, which will relate that high order discretization according to the Nystrom method to corresponding higher order method of moment scheme exactly. When I say exactly, for numerical purposes with machine precision, you can relate 5th order Nystrom scheme to the 5th order method of moment scheme, which utilizes vector basis functions. Okay. Now, there is basis reduction in that. There are all kinds of complications, but what you need to understand that in principle, those two methods are tightly related. Okay. Now, using the high order method of moments may come with large number of benefits. The biggest one of them is imposing some physics-based constraints, such as, for example, continuity of current between elements of your mesh, which eliminates some of the poor spectral properties from your matrix equation. Okay, so there is potentially a huge benefit in using higher order method of moments as opposed to locally corrected point-based, say, Nystrom method, because of additional physical constraints you can put into those basis functions. That's a short answer to that question.
Thanks a lot.
Thank you so much, Professor. So is there any other question? We still, I think, have a few minutes if anyone wants to ask a question.
I wanted to ask a question here. So this is a perfect slide to actually start it, because one of the most important points from the practical point of view here, and we haven't talked about it, is that we need error controllable geometry representation. That's kind of a given starting point. And there are lots of reasons why simulations for certain designs don't have error controllable geometry representation, starting from impossible or poor CAD practices in the companies, or going towards, let's say, that in our manufacturing we have such a big gap in accuracy of what we design to what we reproduce that there is no point for an error controllable representation to begin with. So of course it would be good for us as promoting higher order solvers to promote good practices for CAD engineers to give an error controllable geometry representation. However, that's not the case for a lot of things. So then my question, are there good things about benefits of the higher order solvers in for the geometries where we don't have error controllable representation and basically bad representations to begin with? So are those methods good, or we are basically back to stick with low order methods where we're getting our 2-3 digits of accuracy?
Well, Anton, thank you for this question. That question is actually very sensible and brings up the practical point of, okay, if I don't know my geometry better than 2 digits, why on earth would I struggle for 6 digits in my solution, just to rephrase that, right? So there are different aspects to it. If you, for example, have a high dynamic range in the problem, let's say you do not know the geometry well, but you know that due to, say, large electrical size, the dynamic range is very high, right? And in the interconnect modeling problems, or what I was showing here in the problem of resolving fields on the shade area versus lit area, right, on the electrically large targets, we have this high dynamic range. And what can be done with lower solvers is construction of the matrix fields, if you wish, which are done to accuracies on par with what you require from your dynamic range. And then resolving the rest with the density of the mesh, with the order H type of drop in the error. And that could take care of a lot of engineering problems where this high accuracy is required, but the high accuracy is really stipulated by high dynamic range, not as much as the high order solution in itself, right? So I would say in these kind of scenarios, you have to be judicious in your choices. And Sonnet software, I think, is a very good example, as you know it, right? Which has fairly poor discretization, right? It's not even first order, right? It's like staircase base functions. But the matrix field is done to machine precision if they want to. And that allows them to resolve interactions down to 80 dB, 100 dB with reasonable accuracy just because matrix elements are computed so accurately, right? So in that sense, yes, in many cases, you don't have to go with everything higher order, everything error controllable, right? You have to really pick and choose depending on application. What do you want? What do you need?
Thanks a lot, Vladimir. I think you bring an exact point where high order stuff is still valuable, even in the lack of the perfect information about your geometry.
Yes, yes, and thank you for bringing it up, because it's a very important point, because saying like, okay, I want like a micron resolution on the model of the airplane, the geometry, you don't have it, right? You have manufacturing tolerances which are not getting you there. But there are other factors to consider.
Great. And I think that would be the last question. Reza is asking, is it true to say singularity extraction in higher order method of moment is more challenging than in comparison to locally controlled Nystrom approach? Could you elaborate on this?
Well, with the singularity extraction, if we extracted singularity, which we could, there is no issue, for example, if in taking our electric field integral equation, we know Green's function analytically, we know singularity in it analytically, we can extract it, no problem there. The challenge really is taking that singular part of your Green's function and then integrating it over curvilinear elements. With low order meshes, like RWG method of moments, first order triangles, for example, or first order quadrilaterals, you can take 1 over R singularity, or really R to the power P, right? As long as it's integrable, non-divergent integral, there is an analytic formula for evaluation of the integral with that singularity over the element. And that's why the singularity extraction technique, is so popular in the lower methods. As soon as you move to the higher order method, you can extract singularity, but you cannot construct the formulas. Again, I should be careful saying you cannot construct it. There are no techniques for general curvature of the elements where you could integrate, say, 1 over R on it. And that's why the approach with extraction doesn't take you anywhere further than what you start from, because ultimately you again need to integrate that extract the singularity of the curvilinear patch, which is just as difficult as original Green's function. So, Reza, I don't know if it answered your question, but that's the reason we don't extract singularity in those higher solutions, but we mitigate it through other means. And as a matter of fact, I need to bring up here and actually advertise the work of Professor Sideris, which I'm much appreciating and hoping to reproduce it in my group as well, where he is constructing the Nystrom method with Chebyshev polynomials, and he is killing the singularities through properly constructed bases. Instead of doing local corrections, he can kill those singularities by properly constructing bases and avoiding a lot of complications which we are encountering in the local correction schemes. So I would advise folks who are interested in this type of issues to look at Professor Sideris' work and see how it's done there.
Thanks so much.
All right. Thank you so much. Okay. So with that, we conclude tonight's talk. Thank you so much again, Professor, for giving this really interesting talk. I myself really need to go back and watch this recording once again to just make sure I followed everything. It was a great honor, and thank you all for attending this talk tonight.
Well, it's a pleasure, and once again, thank you for the invitation. Thank you everyone for attending, and great to see my old friends and colleagues here and meet the new people. So all the best to everyone. I'm available over email. If there are questions, please just ask.
Thank you so much.
Thank you so much.
Bye, everyone.
Bye.
Bye, everyone.